So suppose you want to differentiate an expression such as this on the right. So you have 2x plus 3 times x squared minus 1. Now we know if you want to differentiate a polynomial, it's quite simple. If you have something in the form of ax to the power of n, and you want to find the derivative of this with respect to x, it's quite simple. We know that the form of the derivative should be a times n times x to the power of n minus 1. So what we did was we just simply put the index to the front and made this index over here one less than what it was originally. So when you want to differentiate this one over here, then what you need to do first of all is actually expand this, because we know that to differentiate an expression such as this, or in the form of ax to the power of n, we're going to need to have all of our terms separated by just plus or minuses. Over here there's a multiplication in between. So we're just going to expand y. So we get 2x times x squared. This is 2x cubed. 2x times negative 1 minus 2x plus 3x squared minus 3. And so if you want to find the derivative with respect to x, then what we're going to end up with is, so 2x cubed is going to become 6x squared. So decreasing by order, we're going to work with 3x squared next. So 3x squared is going to be 6x. And next up we work with minus 2x, which becomes minus 2 in our derivative. So not too bad. I mean, there is the extra step here where you do need to find an alternate form of y before you can differentiate. Now, you'll see that there are some limitations with this method, because if, for instance, this x squared over here was somehow, what if it was e to the power of x? Then doesn't that mean when you have 2x times e to the x that you're going to end up with some sort of product over there? And you can't differentiate this product using this rule. It doesn't combine both x to the power of n as well as e to the x. It doesn't have these two. So we're going to need to explore a new rule here. This is what we call the product rule. So in the product rule, what we're going to assume is that if you want to differentiate a function h of x, then what you're going to need to do is separate this function into two separate functions. So these two functions are going to multiply by each other. So you have f times g over here, and the derivative function isn't simply just finding the derivative of f and derivative of g and multiplying them together. So we're not going to do this. I'm just going to scribble this, just emphasize. So what the derivative actually is we're going to, first of all, let me just bring a highlighter out. So this one over here. Oh wait, or this one. Okay. So what you're going to need to do here is differentiate one of the terms. It doesn't, one of the mini functions. It doesn't matter which mini function you do first, but I'm going to differentiate the first one, or the one in front first. Just to, a subtle reason for this is it becomes consistent with the quotient rule, which we deal with a bit later on. And you want to multiply this by the original function, g of x. So this one over here, to use a different color, will stay the same. So this one over here stays the same. And you can see over here that f of x over here now stays the same. So the function that was, or the little mini function that was derived at first, now stays the same in the derivative function. So you're going to add the product of the original mini function, or the first original mini function, and then you're going to find the derivative of the next one over here. So find the derivative of g of x. Okay. So alternatively, you can use another notation for this. generally this is when you want dy dx and your original function is in the form of y. You can imagine that instead of having two separate functions, you can substitute to make two appropriate substitutions for two things multiplied by each other. So for instance, if we refer to example at the top, then you're going to have let's see, so it was, let's just scroll back up, so 2x plus 3, so this would be your u, this is your u term, and you're going to also have the v, which was x squared minus 1. And what you want to do here is pretty much the same procedure as what we did with the function notation rule. So the derivative is really the derivative of the first part. So I'm going to get the derivative of u with respect to x. So in this part you get 2. Then you need to find the derivative of v, sorry, the original v, and just slot it in over here. And we keep u this time and then derive v and multiply it by u. And you want to add these two together. So we'll try it out with the example at the top. And we'll just see if this makes any difference to, let's say, our efficiency. Okay, so I'll just draw a straight line here, just to say we're using a different method. Okay, so over here, I'm going to say that I'm going to let u equal to 2x plus 3, v equal to x squared minus 1, so that y is really just equal to u times v. Okay, so when you find the derivative here, then all we're doing is really dy dx is equal to the derivative of u. So we're going to get 2 multiplied by v, and we're going to add u by itself, 2x plus 3, multiplied by the derivative of v, which is, well, derivative of x squared is 2x, derivative of negative 1 is 0, so that's all it is. And if I just scroll down a little bit, squeeze this in, and simplifying all of this will give us, let's see, it'll give us 2x squared minus 2 plus 4x squared plus 6x. And you can see that these two are really just synonymous with each other, because remember that you can just group the like terms here and say that you have 6x squared plus 6x minus 2, which is the same thing. Now, of course, in this first example, it's actually, in terms of efficiency, it doesn't actually change too much. But as I mentioned before, if and what if inside the bracket you had some sort of complicated function, maybe you had a trig function or an exponential, and there's no set rule for these ones over here when they're multiplied by a polynomial. So this is when the product rule really shines, and we'll go through a few examples of how these can be used. So in this first one over here, we want to find dy dx when y is equal to this. Now first of all, you can clearly see this is just x cubed times cosine x. And if they're multiplied by each other, this is the big Q for you to separate it right where they multiply. So what we're going to do over here is we're going to say we let, so this one's u equal to x cubed, and v, we're going to let cosine, or v equal to cosine x. Okay, and from here we're going to say that dy dx is going to be the derivative of x cubed. So I'll just write the derivatives in a different color. So derivative of x cubed is 3x squared multiplied by cosine x. Remember, we leave b as it is, first of all, and then we're going to leave u as it is from before. So we have x cubed, and then we differentiate this one. So you can see that each of these are going to be differentiated once, but in different places. And over here, this is negative sine x, which is the derivative of cosine x. Okay. So just to clean this up a bit, we get 3x squared times cosine x. And accounting for this negative over here, we get minus x cubed times sine x. Okay. Alright, so let's have a look at this one. Now, we're pretty much the same method. You can see here that there's a multiplication sign right in between. So that's where we're going to separate. Now, this one can be u. This one can be v. And when I say this one, I'm talking about this whole bracket over here. So we start off by making our substitutions. So u is equal to 2e to the 3x. b is equal to 5x cubed minus 7x squared. So finding the derivative, we know that we have to differentiate the first one first, or differentiate u. That's generally what we're going to say is the first part of our product. So this is going to be, let's see, so we know that we keep the index and the base, and we use this index over here, and we find the derivative of this index. So we have 3 over here multiplied by 2. So 2 was already there, so we're going to get 6. So this is the u dx, just to be clear. And then we're going to leave v, 5x cubed minus 7x squared plus, and we're going to leave u this time. So u is going to be 2e to the 3x, and differentiate v this time. So we get, let's see, so 3 times 5 is 15 x squared. 2 times negative 7 is minus 14 x. And this one over here is dv dx, or the derivative of v with respect to x. So that's why it's the derivative of this one over here. And if we're to finish this up, a few things you can do here. Now, it's quite subjective on what the simplified form is, but you can see over here that there's a few things you can take out. First of all, the first thing you can take out is e to the 3x and the 2. So that's what I'm going to do. Now the reason why I leave a space here is I can see that in both brackets over here that there is a common factor of x among all of them. So I'm going to take that out as well. Leave this in square brackets because I know I'm going to need smaller brackets from here. And if I take 2x e to the 3x from the first big term over here, I'm going to be left with 3 multiplied by 5x, not cubed anymore because I took a factor of x out but squared, and 7x squared turns into 7x. I'm going to add, now this 2e to the 3x is now becomes a 1 because I took away 2e to the 3x over here, plus, so we get 15x minus 14. Okay, so we're just going to use a little bit more room here, so it's actually a little bit longer than I thought. So over here, you can actually go a little bit further by just collecting your like terms. So in this new bracket, I think I'll just keep it all in polynomial form. So keep my quadratics together, so get 15x squared. My linear terms, so over here, 3 times negative 7x is negative 21, or negative 21x, plus 15x is going to give us minus 6x minus 14. Okay, and that should be the end of that. Or yeah, it doesn't look like there's any common factors here. We're just going to leave it at that. Okay, so I'll just use a different color here just to make sure we're on a different problem. Okay, so find the derivative of our function h when h is equal to this over here. Now, when you're faced with two trig functions multiplied by each other, it's quite clear that it's a product rule problem. So over here, the only difference is that it's in function notation. So recall that h dash can be equal to f dash times g plus f of x times g dash of x. And that's of course if you have f of x here and g of x over here. Okay, so over here I'm just going to say that all of this is f and the sine term over here is g of x. Okay, so this means that when you evaluate h dash, then we're going to take the derivative of the first one here, tan of half x. So tan of half x, so to do this, remember that the derivative of tan is going to be cosine squared of the angle inside the bracket. So we have half x, and we take the derivative of what's inside, which is half, chuck it on top. And g of x over here, we're going to leave it as it is. Get sine e to the 4x plus, we're going to leave f of x now, so leave it as it is as tan half x, and the derivative of g of x over here, this one is going to be a little bit bigger, so we know that we have to leave, sine turns into cosine, e to the 4x in the bracket there, a little bit messy, and over here, what we slot in front is the derivative of what's inside. So we have e to the 4x, and what goes in front, well, the derivative of e to the 4x is really just this, but with the derivative of what's on top here. So the derivative of this is just 4. So that's why we put it in front. Now it's just a matter of cleaning up the algebra a little bit. So over here. Now what we can do with the half is say that there's a 1 on top, and we're going to chuck the 2 into the denominator. So if you have 1 times sine e to the 4x, that's going to be left at the top. 2 from the half goes to the bottom. Cosine squared half x plus, let's see what we have here. Doesn't look like we can do much with this one actually, but sometimes it's probably a little bit better to keep the trig terms together. So I'm just going to put the 4e to the 4x to the front, and then write my tan and cosine term. Okay. Looks like a really complicated derivative in the end, but this is what it would look like in one of its more simple forms. Of course, you can use your trig identities here a little bit to further manipulate this expression, but this is pretty much as far as we can go.